In Unit 7, opener number 12, we're going to be looking at finding the domain of a bunch of different functions. The natural domain is the largest set of inputs for which the function or relation has meaning. A lot of times when I'm asked to find the domain of a function, instead of thinking about the possible inputs that do work to satisfy a given function, I try to think about the possible inputs that don't work to satisfy a function. Then I can work around that and say, well, all of the other inputs except for that one work as inputs for this function. I'll show you what I mean as we look at the first example. Y equals 6 over x. I can think of tons and tons of different inputs that I could substitute in for x that would work as possible inputs for this function. So instead, if I think about what I'm not allowed to have as an input for this function, I see that I'm dividing. The only thing that I'm not allowed to divide by is 0, because dividing by 0 will give me an error. So when I'm coming up with the domain for this function, I say that x can be any real number, anything that I can possibly think of, except it's not allowed to be 0. So x is any real number except for 0, and that's the domain of that first function. As I move on to the second function, I'm faced with a similar situation because I have another division problem. So when I look at what's in the denominator, I need to think about what values x is not allowed to be. So I need to think about what will make me divide by 0 for this function. So I know that each of these factors in the denominator is not allowed to equal 0. X plus 2 is not allowed to equal 0, and x minus 7 is also not allowed to equal 0. So if I solve both of these, then I'll come up with my two x values that will not work in the domain of this function. X cannot equal negative 2, and also x cannot equal 7. X can be any real number except for negative 2 and except for 7, because when I substitute those in, I'm dividing by 0, which gives me an error. As I move on to my next batch of functions, I see that the first one, y equals 5x plus 9, is just a linear function. I don't have any division like I had in the last problem. So again, I'm going to start by thinking, is there anything that I'm not allowed to plug in for x? So I'm going to think of all different types of numbers, like positive numbers. Nope, that's allowed. I can input positive numbers. Negative numbers. Nope, that's allowed. I can input negative numbers. 0, fractions, decimals, any of those are appropriate as inputs for this function. So that tells me that there's nothing that x cannot be. So that means that the domain of this function is that x can be any real number. There's some fancy symbols that we can use for that if we don't want to write out that x can be any real number. What that looks like is x is an element of the real numbers. Element is this little squiggly e. And then the real numbers, the symbol for that is a big fancy R. So that says x is an element of the real numbers, or x can be any possible real number. Let's take a look at part D and see if that works the same way, even though there's absolute value bars. Can I input positive numbers? Can I input negative numbers? Can I input 0? Can I input fractions and decimals? Again, it looks like even though there's absolute value bars, any of those different types of inputs that I might want to substitute in are all fine. So again, x is an element of the real numbers, or x is any real number. When I move on to part E, I see that now I'm faced with some square roots, so that means that I probably am going to have a few things restricting my domain on this one. So what I want to do again is think about what will not work as the domain for this function. So let's think about square roots. Can we square root positive numbers? Yeah. Can we square root 0? Yeah. But we can't square root negative numbers because we don't get a real number back in return. So that's what we need to think about. So in order for this to work, I need to make sure that I'm inputting values for x that give me 0 or positive numbers to take the square root of. So the way that I can figure out what those values are that satisfy this is I can take my 4x plus 9, and I know that 4x plus 9 has to either equal 0 or a positive number. So that means that 4x plus 9 has to be at least 0. If it's greater than 0, I get a positive number. If it's equal to 0, that's okay, because the square root of 0 is 0. The one thing that I don't want is to take the square root of a negative number, because then I get an imaginary number instead of a real number as my output. You'll learn about that in later math classes. So I'm going to solve this quick inequality, take away 9 from both sides. So 4x is greater than or equal to negative 9, and divide both sides by 4. So my possible input for this function is that x can be any real number as long as it's greater than or equal to negative 9/4. Finally, part F combines what we were thinking about with fractions in parts A and B, along with what we were thinking about with square roots in part E. So I'm going to take a look at the denominator of the fraction, and the first thing that I know is that the denominator of a fraction cannot equal 0. So I think that's what I'm going to eliminate first. I want to think about what possible values I could substitute in for x to get 0. X squared minus 25 cannot equal 0. So I can bring my 25 over to the other side. X squared cannot equal 25. And I have to remember that there's actually two values that I could square to get 25. X cannot equal 5, and it also cannot equal negative 5. So x cannot equal plus or minus 5. So that we know for sure. But we also need to think about our square roots, and we need to make sure that not only in this case can we not have 0 in the denominator, but we can't have anything that's going to give us a negative underneath our radical. So we need x squared minus 25 to only give us positive numbers. So let's think about different numbers that we can plug in. We know now that we can't substitute in 5. But what if we substituted in something bigger than 5, like 6 or 7 or 8 or 9 or any of the decimals in between? Well, that would be okay, because I would get the square root of a positive number. But if I try to substitute in values less than 5, like 4 or 3 or 2, then I end up getting the square root of a negative number, which is not okay. So I see that my x values have to be greater than 5 for my domain. But then we also have to take our negative 5 into consideration. Negative 5, when I substitute it in, would give me the square root of 0 in the denominator, which I don't want. But if I try numbers like negative 6, negative 7, negative 8, negative 9, those work. Those give me positive values underneath my radical. So I have to be really careful, though, when I write this inequality. X is greater than 5, like numbers like 6, 7, 8, 9, etc. Or x is, I don't want to say greater than negative 5. I actually need to say less than negative 5, because negative 6, negative 7, numbers like that are actually less than negative 5. We always have to be a little bit careful when we're dealing with inequalities with negative numbers. So this is our domain of function f. X can be greater than 5, or x can be less than negative 5. X cannot equal 5 or negative 5 because we don't want to divide by 0, and x cannot equal anything between negative 5 and 5 because we don't want to take the square root of a negative number. So I'm going to leave you with a few pieces of advice when you go to find the domain of a function. I would say that first you want to think about values that do not work as possible inputs for x. Even though the domain of a function are all of the values that are possible inputs for that function, it helps to think about what doesn't work, and then you can work backwards and say in turn what does work. And when you're thinking about values that are not possible inputs, remember these two things. You cannot divide by 0, and you cannot take the square root of negative numbers if you want real numbers as your outputs. That should be a good start to get you thinking about domains of all different kinds of functions.